inside here is a rectangle. So from here to here. Now, how do you find a rectangle? Is length times width. So my area is equal to width or length times width. Length times width. Now, if I take and multiply this out to find my area, I'm going to get area is equal to 12x minus 2x squared. If I follow that through, right?
Yeah.
So that stands for the area of that cross-sectional area. Now, I have to maximize. Now, maximizing, where does the maximum or minimum always occur? At the vertex. So to maximize this equation, to find the maximum, I'm going to go on negative b over 2a. Now, noticing that this equation is not in standard form, my a on here is negative 2. My b is 12. So therefore, if I plug that in here, I got a negative 12 over 2 times a negative 2. So I get a negative 12 over a negative 4, which is 3. So that's my x. 3 is how much I would have cut out. Now it says, what is the area? I'd plug it back in. Area is equal to 12 times 3 minus 2 times 3 squared. So you got 12 times 3 is 36 minus 3 squared is 9 times 2 is 18. I believe I end up with 18 inches squared or whatever it is.
I did it differently, but I got the same answer.
So how did you do it?
I took my 12 minus 2x and set it to 0. And got x equals 6. And then I took the leftover 6. I had 6 divided by 2 to get my 2 x's on the top. And I took 6 times 3 to get my area.
Why did you divide by 2 though? I mean, what would 12 minus 2x? You got 6.
I got x equals 6 for the bottom. And then for the 2, I had 6 left over for the 2 x's. So I took 6 divided by 2 and got 12 x's equal 3.
Okay. Okay, now it's right. You get the right answer that way. And I guess the easy way to say this is it'll work if it's a square. Your case will work if it's a square because to maximize anything, the best maximum case is a square. Okay? That means if they cut, the case you have, if they cut on the same amount from both sides. Okay? Now, if I change this problem and say from one side I'm cutting x and the other side I'm cutting a half x, that's going to screw your whole scenario up. Okay, so I'm just saying you got the right answer, but it's a one-case scenario. Okay? I want to think about when you're doing these problems, I always want to think about how to find the maximum. And the maximum always occurs at the vertex. And sometimes when you solve a problem down, and I see this a lot, you might get the right answer, but you might get the right answer because the problem is set up that way. I guess the easy way to say it, that you do 2 wrongs make a right, I guess you can say, go through it. But that's kind of where we're at. I want you to try another one for me before we move on here. I want you to try 69. I would just start with that helps you. Nothing kind of picture. Well, the same kind of picture, but they don't have that middle fence in there. What do we got? Anybody got anything? Okay, so we're starting off like that. That's a good way to start. 2L plus 3W, he says equals 600, right? They get 600 feet of fencing. You know, if I'm going to write a quadratic equation, I'm going to write an equation for anything. I need to have one variable, right? Right now I have two variables. 2L, I got three of the W is going across and 2 of the L, right? Let's write another equation. Area, let's set the area, equation for the area of this figure. Area is equal to, is that? What is that? Length times width? Length times width. And what are we maximizing? Area. So we're going to have to work with that formula, but right now that formula has two variables. So we have to substitute one of the variables in. Doesn't matter which one. I'm going to substitute in for L. Okay? Now how am I going to get an L? Do I know what L is? No. Kind of. Let's see L by itself.
Multiplied by L.
So the subtract 3W for subtract 3W, so we get 2L is equal to 600 minus 3W divided by 2. So I get L plus 300 minus 125W. Do I know what L is? Yeah. So plug it back in where? Length times width. So I'm going to write area is equal to my length, which is 300 minus 1.5 W times W. Bring it through the parentheses, I'm going to have area is equal to 300 W minus 1.5 W squared. Right? Now I had length times width up here, so what I did is I took my length, plugged it in. Okay? Now, do I have area in terms of W? I have area in terms of a quadratic. So now I want to maximize it. Where does maximum occur at on a quadratic? At the vertex. So let's find the vertex. Negative B over 2A. My B is 300. Over 2 times A, so negative 300 over negative 3, which is 100. So that tells me what variable? W. So this tells me my W is going to be 100, 100, 100. So and the other side would be 150. Now, how could I get to 150 easily? It's just take that 100 and plug it in here. I'll get my L. Okay? And what's my area?
600. Oh, that's just 150 times
150 times 100. My area is going to be 100 times 150. By just changing that one dimension a little bit, it kind of changes, throwing that extra fence in, it changes it away from a square. Not a square anymore. No, it's a rectangle.
Could you do it without that fence in there?
Yep. Let's do it with all two sides in there. Let's look at number 65. Down to 65, very similar. There's many ways to do this problem. I set up this way so we can see what it has. What I know is this. Everybody has something like this. Without what I'm drawing. The drawing's a sideways, but the drawing has dimensions for you, kind of, right?
Yeah.
But how do you get them is like this. Is if I wrote this down, I have 2W plus L, we know equals 600, correct? If I subtract 2W off both sides, I'm going to get L is equal to 600 minus 2W, correct? Okay. Now, area of this is what? Length times width. Correct? So now my area is length times width. I know what L is, so my area is 600 minus 2W times W. Right? Bring it through the parentheses, I'm going to have area is equal to 600W minus 2W squared. Now, vertex is at a negative B over, so I got a negative B, which is over 2 times A, which is a negative 2. Correct? So, negative 600, negative 4, which is 150. So if I know that, that deals with my W. My W is 150.
I think the area is 100.
What?
So W.
W is 150. I plug it back in. L is 300. Correct? How could I do this a different way?
Could you minus L and divide
Yeah, you can got W by itself.
I did that way.
How could I set it up differently? Oh, I got one. I was just gonna do it. Yeah. Let's say.
Let's make it really fun.
Extra.
All back to the possible.
Here's my house.
Okay, let's say next to QW.
Yeah, I was gonna do
Hey,
No, then the house should be W.
I had. Let's go like this. Here's my house. this is W, this is L. This is 1/3 W, this is 1/3 W. My house goes there.
So you're gonna have
House is
that,
also 1/3.
so you're gonna have,
So-
1 2/3 W plus 2L.
Can we just set it all up to W? Or all?
So now what I'm doing is that
Minus
600 meter
minus
fence, got 600 meters fencing.
Two,
Can we just have W
wait,
minus 1/3?
600, how much fencing? You would do,
Can we have L, L, W, and W minus 1/3?
Well, you could do that for your 3 sides, but if you're adding up sides, you get your length, it might be easier to go 2/3 W. Okay, let's try it. Get 600 meters of fencing, maximize the area.
1 2
I guess it's a lot.
600.
Ms. Fisher, it was half of 1 2/3.
Well, half of 1 and 2/3.
Yeah, what is it?
5, 6.
Yeah, well, you know, 5/3.
Half 5 is 5, 6.
Stupid.
When I set it up, I got this in my equation. I went 5/3, but it's 1 and 2/3. Right? 1 and 2/3 W plus 2L equals 600. Most you probably got L by itself again. 2/3 is equal to a negative 5/3 W plus 600. 5 by 2. L is equal to negative 5/6 W plus 300 if I divide by 2. And actually, it probably might have been easy to get W by itself, but I don't know.
No, I tried that. It got 2.
Now, area, that's my L, so I got negative 5/6 W plus 300 times W.
Near 5/6 W's.
Plus 300 W, right? Not much different. Negative B over 2A, find the vertex, so negative 300 over 2 times a negative 5/6.
If you get negative 5/6 divided by 2.
How do I get a negative? Divided by 2 is
Negative
times it.
5/3.
I mean, you got 5/3 and divided by 2 is the same as times it by a half. So we get 5.
That'd be negative 10.
That'll be a negative 10/6. Divided by negative 10/6. So I'm going to do it off the side here. I got negative 300 times 6 over 10 negative, which is equal to 180.
That is our
W.
W.
That's my W, 180 is my W.
The other 60.
This would be 60, this would be 60, I had 600 meters of benching, so that'd be 300, these are 150.
Yeah, sure.
So,
So maybe
in
it's
many
it's
ways,
a square yard then. No.
no, it's not a square yard. There's many ways you can write this, you know. I could change this problem again, you know, we're talking about maximizing, minimizing a quadratic function, right? I could write an equation and say this, let's say I give you, we're not gonna do this one right now, let's say I give you a cube, or a prism. A prism, a rectangular prism, and they say the sides of the prism are 6x and x plus 7. Maximize the surface area. You know, find the surface area means find the area of both sides, right? So maximize the surface area. I can say maximize the volume. You know, there's a lot of ways you can write these problems, and all you have to make sure is there's two sides or two things you don't have. It won't be hard to change them. This is what I mean by applying it. Just because I give you one type of problem, know how to apply another type of problem to it.
Wouldn't it be a square? Because it's 300 and half of 600 is 300, so the other two halves.
Is this a square, you said?
Well, no.
If it was just
Without the house in there.
without the house, it's always a square. That's why I always say show it work, because if I told you I have a four-sided figure and it says maximize the area, it's a square every single time. Well, everybody's gonna say, okay, 120 divided by 4 is 30, okay, there's it. My answer is 30 by 30. That's why I want you to show me my work, because it's not all, I wanna show you how to set up a problem. Because what happens if it's not a square?
You're wrong.
Then you're wrong, and then now what are you gonna do?
Right.
Most of the time, cry. Yeah.
Okay.
So
Right.
so that's kind of why I want you to understand the process as you go through. So, okay,
Depends.
me too.
Only a joke of the day right now. Joke of the day.
Polynomial functions and their graphs. I'm gonna jump ahead. Smooth, continuous function. We got a lot of rules we're gonna talk about.
Do you want to understand?
You'll have to do that hour.
Were you there test today?
Why not?
We're going.
You don't think
People
so online?
Well, they're online right now.
Take pictures of them.
You can look at them anytime you want, but it's I'm not handing out in class.
That's what you talk about later.
Yeah.
Déjame my card allá.
Okay. Definition of a polynomial. This is where it changed. We just did all the quadratics, which you think about last year or year before. We did quadratics for about 6 or 7 months. But we just did that in one day. So we did last year. So we did all the quadratics. Now we're going to go on to a polynomial function. And it says, let n be any consecutive non-negative, let n be a non-negative integer, and let a of n minus 1, so on, be real numbers, and a and n cannot be 0. The function defined by this equation is called a polynomial function of degree n. The number a of n, the coefficient of the variable, is the highest power, it's called the lowest coefficient. Now that's the definition of the book. Now, if you read underneath it, it says, polynomial of a function's degree 2 or higher have graphs that are smooth and continuous. Degree 2 or higher, okay? Quadratics are degree 2. What I mean by degree is the highest exponent from. Okay? Degree 2. If it's a cubic equation, it's degree 3. If it's a quartic equation, it's degree 4. If it's quintic, it's degree 5, right? Higher you go. If it's degree 6, it means it's the highest exponent is a 6. And it says anything of the higher degree of 2 is a smooth function. And it says by smooth, we mean that the graphs contain only rounded curves with no sharp corners. By continuous, we mean the graphs have no breaks and can be drawn without lifting your pencil. No, so like Truman asked me yesterday when we did a quadratic and we graphed them out. He said when we draw that quadratic, we come down and we do a curve, right? It doesn't come to a point, sharp point. All polynomials will have curves. They will not have points to them. It's a smooth curve. It's very important to know the difference between a graph like this and a graph that looks like this. Very important to know what the graph would look like. You know? Reason being, first graph here, the majority of, I don't care what major you're going to go into, you're going to see some calculus you're going to go into. When this is the basics of calculus. In calculus, all your calculus concepts will work for this graph, type of graph. Anything that's smooth and continuous. Your calculus concepts are undefined for this graph. They don't work. So if it has a sharp corner, calculus blows up. That's why we have to know the difference between a sharp corner and a curve. I mean, it sounds like a very simple concept, but that's what we have to know the difference. And when I say you might be taking calculus, maybe I'm wrong. Maybe your majors don't have it, but a lot of them do. I was surprised. I had, like I said, I had my one friend taking accounting major or something like that, and they're doing statistics, which is common. But now a lot of the statistics they do in there all deal with calculus concepts, so you have to have calculus first. So I was like, oh, okay. I couldn't do it. I couldn't remember all those. And calculus is fun. I asked some calculus good. Who would take in calculus? So, not my side. I just wanted to college. There was another one. That's more interesting. I heard one the other day. I can't remember what it was. Took the first test, got a C on Wednesday. Good job. I figured I got a C. I didn't study much, so I studied like mad for the second test. And the person said, and I got 20 on the second test. So.
What does that mean?
I mean,
Don't study.
he studied like mad. He said, yeah, it's more. Calculus is hard. And I mean,
How many people are in calculus classes?
this year here,
Yeah.
10. We're doing good. Calculus is fun. For me, we have a big advantage. Is that?
When they go to Valley Fair.
Well, they go to Valley. Actually, we're trying to have a big trip. But,
Where are they?
but
Where are they going?
we're talking about like Valley Fair, a couple of restaurants, Twins game. I don't know. See what we can pop on Facebook and ship the whole works.
I want to be a coach.
So we're not doing much of it, so. But I mean, calculus in high school is totally different than college. I'll give you that. Because what we are doing in high school, you do in one semester. We're doing it all throughout the whole year, and it's slow. It's like this week I came back. I can't do that in here because we have so much. But in that class, I came back from vacation. It's like I don't feel like going on yet. Let's take the whole week of review. So we just took the whole week.
Oh, yeah, because I'm hearing here.
So, and actually, we're so far ahead already. So I don't know what we'll do for the rest of the year. We'll find something.
Some burgers.
Oh, we're having that too. Graphs of polynomial functions. We're used to quadratic graphs. We're going to get a lot of different ones. This one looks like a basic cube graph. Like I said before, remember it is smooth. Going around it. This is like an x to the fourth graph. Notice that both arrows go up here, come down. It's not symmetrical. We're going to learn how to tell if it's going to be symmetrical or not. We're going to learn how to tell if it both goes up or both goes down as it goes through. These are graphs. We dealt with some of these before. Piecewise functions. We have a jump in here. Causes the trouble. Notice here you got a sharp curve here, you got a sharp corner here, and you actually have a cusp there.
Cusp?
A cusp there, and a cusp is a cusp. It makes it not smooth. A cusp you can't see it very closely there, but what it looks like is this.
So what kind of formula would that be?
What kind of formula? That's more of a piecewise function.
What causes the cusp?
It's a piecewise function.
So there would be no
There would be.
exponent?
Oh, it could be an exponent.
Piecewise.
Piecewise function. It could be another option for the absolute value function here is a sharp corner. That's one sharp corner. Another one is which function we haven't dealt with yet. Another graph that has a lot of these kind of shapes is a tangent inverse graph. Some trigonometry functions. So a lot of those have sharp curves to them. So we're going to look at, now this is kind of like I said, I kind of jumped ahead a little bit. I said after this chapter, everything is new. And actually, I should have said after that yesterday's section, everything is new. And we kind of start right now is, have we dealt with much functions over x squared before? Some of you guys have, but not many. We haven't dealt with it. So this is going to be kind of a lot of the new stuff as we look at this. Looking at smooth curves. You know, and looking at what we have for roots as you go. End behavior. We're going to give you the basic definition of end behavior. There's two types of end behavior we're going to deal with. One deals with end behavior in pre-calculus, and one deals with end behavior, how to solve it in calculus. Pre-calculus, what we're going to say is end behavior means what's happening way at the end of the graph on both ends. When you think of graph, you really have two ends, don't you? You got to end way at a positive infinity, and you got to end at way at a negative infinity. When we talk about end behavior, what sounds weird is we don't really give a crap what's going on right in the middle. It can go all over the place. When I ask you end behavior, I'm just asking what's happening way out there. So for example, I might have a graph that looks like this and say my graph might level off at 2, let's say. My graph might level off at 2. Okay? And it might level off over here at let's say a negative 2. Okay? So my graph is getting closer and closer to 2 and negative 2, going one way or another, right? What's happening in the middle? Really don't care. My graph can go like that. I don't care because I'm looking at the end behavior. It can be all over the place. We will get to graphs like that too. So we will though, but what we're looking at end behavior is what's happening way far off. So here's our cases. The leading coefficient. Yes, the leading coefficient. As x increases or decreases without bound, the graph of the polynomial function, and the polynomial function means any function. It has a lot of cases here. First of all, we're going to start off with n being odd. And what I mean by n is this. If my highest exponent is odd in my problem, you know, you can look at this chart. It's in your book. You can go it, but I'm going to put it, lay it out pretty straight. If my highest exponent is odd, and it's positive, it's going to go up to the right and down to the left. My graph at the end.
So you're going to be your highest exponent is at the...
So like if I wrote an equation like this, x cubed plus 4x squared plus 2x plus 1, my highest exponent is 3. My degree of my equation, another way of looking at it, the degree of the equation is odd. If it's positive, it goes up to the right. If it's negative, it goes down. If it's positive, it goes up to the right and down to the left. Now, when I say if it's positive, that means if the number right here is positive. If the A is positive. Now, same thing, if it's odd and that A value is negative, it flips the graph. So it's going to go up to the left and down to the right.
I know the middle stuff doesn't matter, but does it affect the negative in the middle? Like the middle of the graph is the negative?
Yeah, it affects it, yeah. You'll see all these cases. Well, what our goal is, ultimate goal is, we're going to get to there today, but our ultimate goal of all this section is this. You're used to x squared, correct? That's all you were used to. Now we're expanding. And what we're going to do is when we have, think about x squared. How many answers do you have? How many times across the x-axis? 0, 1, or 2, right? Now what we're going to do is change it. Okay, let's say I give you an x to the 6 equation. How many times is it across the x-axis?
0 to 6.
0 to 6. We're going to find all 6 times. And every time there's a new root, that means it has to change direction. We're going to find out how many times it changes direction. We're going to find out if it goes up to the left both times, round, all this stuff. We're going to find everything about these graphs. And a lot of it actually comes out by not doing any math, really. If I know a lot of these concepts, I can say, okay, if n is even, if my highest degree is even, if I give you the x to the fourth graph, okay, right away I said it's an even degree, correct? X to the fourth. So on x to the fourth, I know that either it's both going up or both going down. Now I can logically think in here, it says if a is greater than 0. Well, if my first term is positive, I know it's going to go, both are going to go up. I always think back to a very simple example, x squared. X squared applies to all even functions. X squared, if it's x squared and a is positive, it goes up, right? Both sides go up. It applies to anything bigger than that, even 2. 4th, 6th, 8th, 10th.
What if it's like a positive number to the third? It's just
So if it was like 3x to the third,
yeah,
okay, let's follow the rule. N is odd.
yeah.
A is positive, right? So it's going to go up to the right and down to the left.
So if you just remember this chart, you won't have to pretty much know it.
Oh, what was that?
If you remember this chart, you'll be some pretty
So-
good. You won't have to.
Oh, I mean, I don't even remember the chart, just know the
So
concept.
if A is
So it's not hard. I always think about it as this. If A is positive, it's going up the right side, right?
Yeah.
If A is negative,
It's going down.
going down the right. You know, so it's not, the negative always thinks about going down, especially, these are easy to remember. Positive going up, negative is going down. That's easy to remember. The other ones are a little bit harder with that. I always think of the cube graph when I think
so, so if it was like a negative x, negative x cubed, it would be
of it. Negative x cubed, okay?
1. So it would look like that.
Just like this. Like I said, doesn't matter what's happening in between when we look at M behavior. It doesn't happen. But now, what we're looking at right now, this is, like I said, this is simple M behavior. What I mean by simple means this. We are saying that it's going up or it's going down. We're not even getting to the point yet of saying if it's approaching a number or not. And that gets to be a little more as what happens at the end. Is there an asymptote out there and so on down the line. Let's come back to that. Okay, let's look at this equation. Very easy one. Using a leading coefficient test, determine the end behavior of the graph. Let's look at it. What's the highest degree here?
So it's going
3
3.
down.
The highest degree is 3. So the highest degree is 3. We know one side's going up and one side's going down because it's odd. My A is,
Negative, so it's going down to the right.
so negative means it's going down to the right and
Up to the left.
up to the left. So my graph would look something.
Like this.
This one actually would look something like this. Something like that. So, I don't know what the middle exactly is. We'll get to that later. That's not a hard rule. That's very, I think that should be straightforward, but it's a new rule. Not a rule that haven't had before. Now, zeros of polynomial. What are zeros?
We're crossing the
X-axis.
Exactly. Okay. Like I said, when we deal with quadratic, it could be 0, it could be 1, it could be 2. Now we're moving up. When we think about my x cubed graph, my x cubed graph could look like this. My x cubed graph could look like this. How many answers do I have?
3.
3. My x cubed graph could look like this. How many answers do I have?
1, 2.
2. 1, 2. My x cubed graph could look like this. 1. There's a lot of options. And could an x cubed graph get 0? No, one going up to the right and one going down to the left. It has to cross the x-axis sometime. So we have to for surely have 1 at least time it's going to cross the x-axis. Not always the easiest to find, but it's always 1, at least 1. If a polynomial function, then the value of x for which f of x is equal to 0 are called zeros. We know this. We have other answers, solutions, roots. Anything else? Answers, x-intercepts, all those. Each real root of a polynomial equation appears as an x-intercept of the graph. When I write x-intercepts, and this is kind of the last test, when I write x-intercepts, I write them as a point. So let's say my graph crosses at 4, 0. My x-intercept is 4, 0. If I ask you for a y-intercept, it is 0, 4. It's one corner or the other. Find all the zeros of x cubed. Now we're gonna get fun. X cubed plus 4x squared minus 3x. They helped you out on this one. One way to find x-intercept is to solve the equation. They factor by grouping.
Well, that's one thing you can do,
What?
really. How else would you do that?
How else can we do this equation? We're gonna see it.
Close, so.
Well, there's like 4 curves, you can't do the quadratic,
You can't do the quadratic.
you can't tee it up, you can't do a lot of things.
We do p over q.
What? I don't know.
Nice.
P over q.
Oh, yeah, there's a trick.
When we do this, now what happens here is quadratic form. Now I'm gonna go back to what Truman just said here. Can't use the quadratic. Why?
There's not 3. There's
You
4.
don't have A, B, and, well, you do have A, B, and C, but you don't have D.
Quadratic only works on
X squared.
x squared. I got my 10th graders thinking right now. I mean, the 10th graders, we talked about the quadratic formula and we're doing factor. I don't need factor. I'm just doing everything with quadratic formula. One thing bad about the quadratic formula is the quadratic formula only works for the quadratic equation. The quadratic equation. So therefore, you do need to know how to do factoring. Because factoring is going to help you do the rest of the equations. X to the cubed, x to the fourth. Graphing and factoring are the two main concepts. Now, if I look at this equation to find my zeros, simply put, I'm just going to walk through. We grouped. How many remember factoring? We talked about it earlier this year, right? I started using this. I always talk about factor by grouping. I always put that rule in there. It should be a plus between here, right? And then factor out what's in common. They did a -3, did a +3. I don't know why they got
Why did they split up this X? Oh, that's what's in common, never mind.
How come
I
there's a
understand it.
plus between?
I'm trying to figure out how they did this one. I didn't write this problem, so because they went in here with this and then they got a negative here, so this problem.
But then how did they end up with an X squared?
That's what I'm trying to figure out.
But shouldn't it be like a?
So this should have been
Should it be plus?
That's wrong.
this should have been like that. So
Yeah.
What is it? So plus and negative? Plus.
so.
Minus 3,
Just remember when you do this problem like this, the main thing I want to point out, I know the work is wrong a little bit out here, we will do some problems. When we get x squared minus 3, the thing you have to remember, whenever you take a square root, you always have a plus and a minus. So you have to make sure you get a plus and minus. That's how you get the plus and the minus on this equation. Bell's gonna ring here in a second. So what I'd like you to do, finish up section 1 if you haven't did your homework yet. Or we got a long ways to go yet.
What's the modal say?
I don't know. I didn't look at it.
Sure. Yeah.
I don't think you'll try it. It says 1 through 49 odd. You can try it. 322, 1 through 49 odd.
What's the page number?
322.
What do you want hand in?
30.
Just 30?
30 is fine.
You want this handed in?
Yep, basket. And your homework in.
For now? Oh, we're kind of in the basket?
Put it right in the basket. Fourth basket right here.